we're working our way through the section that covers descriptive statistics. And so in the first video that we did on this part of the text, we looked at how to find the middle of a data set. And in this video, we're going to look at how to measure the spread or the dispersion of a data set. And so we're going to talk about standard deviation and variance and other things that would be used to measure spread. And we're going to start off with an example. You may recall the data set from problem 24, which is on the screen in front of you here, from the previous video. It's the eruption times for the California Old Faithful Geyser in Calistoga. And so notice the first thing they're asking here in part A is that you would determine the sample standard deviation of the eruption. And so we want to talk about standard deviation. How do you get it? What is it? And what do you need to know about it? And before we get into the actual calculation, we want to make sure that you're clear on a couple of things. So the notation starts to get a little bit heavy in this part of the text. And so what I suggest to most people is that you may want to replicate in your notes something that we used to have in the end papers. So in the end papers of the text, they used to have sort of a glossary, if you will, of notation, where they basically took all of the well-used mathematical notation symbols from the book and they put them into a single table so that you could quickly look up some piece of notation if you didn't know what it meant. And that's gone away for some reason. I don't know why. I sort of regret that it's gone, but maybe it's good in a way because, you know, when you have to physically write something like that down, it helps you to remember it. Research is very clear. It shows that the act of physically writing something jogs the memory. And so what I'm suggesting is that you take note of some of the things we have on this slide here. So one of the conventions we observe in statistics in general, because we're very careful to distinguish between a statistic and what we call a parameter. So in other words, if you take as an example, mean. We showed you in the last video how you would calculate a mean, and I'm sure you know how to find the formula in the text. If you apply that formula to a population, it's called a parameter, and that would be the population mean. If you apply that very same formula to a sample, it's a statistic, and we call it x bar, the sample mean. And so we're always very careful to distinguish between a number that comes from a population versus a number that comes from a sample. And so we use Greek letters for parameters. That would be numbers that come from populations. So we use the Greek letter mu for population mean, and we use the Greek letter sigma for population standard deviation. And we use Roman letters for statistics that come from a sample. So in other words, very same calculation, however, it's designated as a statistic because the origin is a sample. So we use x bar for sample mean, and we use the lowercase s for sample standard deviation, and so on. And so those are things you want to have down, because when you look at some formula, like in this section you can find a formula for standard deviation, it looks like gibberish if you don't know what the individual notation letters in the formula represent. So very important to take note of that, and that's kind of one of those things you want to be proactive about, because trust me, it's not going to get better, it's going to get worse as the course goes on if you're lazy about that. Anyway, let's go back to our example here and see what we need to get. So the first thing that we're going to do here is we're going to find the sample standard deviation as they have requested in part A of the question here. There is some rounding issues that come up, and here they're giving you special instructions. They're saying to round sort of contrary to what the standard operating procedure would be, and we'll have some words to say about that. Now, I already have this data set in my calculator, and if you're following from the previous video, you may well have it in yours as well. If not, it might be a good call to follow along. So in other words, pause the video, key this in, and then let's make sure that we agree on what comes out from the calculator. Anyway. So I have my summary statistics from the previous video, and I'm going to quit this. And I actually had the answer on the screen right there. I don't know why I did that. That was kind of dumb. How do you get sample standard deviation or population standard deviation, whichever you need? Well, you go to the Stat menu, and you go to the Calc submenu, and you're going to use the first one that's lit there. It's number 1, the 1var stats. And so on my calculator, you press Enter. You tell it the list where your data is. In my case, it's list 1. You don't want anything in frequency list. Just leave that empty, and you're ready to calculate. And so we go right back to where we were, having the one variable stats on the screen. Now, there are two different standard deviations, as you can read in the text. We have the sample standard deviation and the population standard deviation. Why are they different? Well, that's also discussed in the text. It has to do with degrees of freedom and estimation and so on. On this screen right here, you can see S sub x, as I typically read it, and that is the sample standard deviation. That's the notation that the calculator uses. And sigma x is the population standard deviation. Why do they add this subscripted x? Well, because you can do this for bivariate data. In other words, you can do it for two lists at once. And so they are distinguishing between the standard deviations for the x values and for the y values. Anyway, there you have your sample standard deviation and your population standard deviation. Which one are we being asked for here? We're being asked for the sample standard deviation. Now, if you recall, the data set that we're using has integer valued data. And the convention for rounding standard deviation is you're allowed 2 places beyond what the data contains. So in other words, here with integer valued data, we would be allowed to round to 2 places, to the 100th place. But because of the special instructions in this problem, we're rounding differently. So we wanted to draw your attention to that. Please make sure you're clear on the rounding for standard deviation. That is one of those things that gets a lot of people. Anyway, let's record what we've got. So if I'm following the rounding conventions that we would normally follow, I would report the sample standard deviation as 6.25. But because I'm following the special instructions in this problem, I'm rounding it to 6. And you'll see why in a bit. In a second, you're going to see that the next part of the question makes reference to something known as the empirical rule. And the empirical rule, in 25 words or less, is a rule of thumb which we use for estimating how much of a distribution you can find within a certain number of standard deviations of the mean. Now, this empirical rule only applies when you have bell-shaped or normal enough data. So in other words, before you can use it, you have to make sure that your data set is distributed in a bell-shaped fashion. And if it is, then you can use the empirical rule to estimate how much of the distribution is within a certain distance of the mean. Now, we have it in a textual version here. You can read that for yourself. What I would suggest is that you probably want to copy down this figure 13 that you can see on the screen in front of you right here. This is a very good illustration, and what it's showing is that if you go out 1 standard deviation, in other words 1 standard deviation below and 1 standard deviation above the mean, that you're going to capture about 68% of the distribution. And similarly, if you go out 2 standard deviations below and 2 above, you're going to get about 95%. And if you go out 3 standard deviations below and 3 above, you're going to capture about 99.7% of the distribution. And so this is a very good general illustration of the empirical rule. And you might want to have this down, because I don't believe you can find this on that formula card that we've talked about before. So anyway, this is going to be used for the next part of the question. Let's go take a look. Part B says, on the basis of the histogram drawn previously, we actually looked at that in the previous video, I'll show you in a second, comment on the appropriateness of using the empirical rule to make any general statements about the length of eruptions. So what are they really asking? Well, they're really saying, look, you're supposed to know that the empirical rule only applies when you have a bell-shaped distribution, normal enough data, in other words. And so they really want to know, is what you saw before, is it normal enough to permit safe or reasonable use of the empirical rule? And I would say, well, yeah, I think so, because take a look. Here's the histogram that we did before, and this is the one with a bin width of 4. And we said at the time that this looked approximately bell-shaped. And so I'm going to go with that, and I would say that the empirical rule is reasonably deployed here. So responding to what they're asking here, they want me to comment on that. So I need to come up with some kind of a statement. So what's my response? Well, the only condition that has to be satisfied in order to use the empirical rule is that the data be bell-shaped, or distributed approximately normally, or distributed in a normal enough fashion, however you choose to put it. And so in this case, we've seen that the histogram is approximately bell-shaped, and so the empirical rule can be applied. Let's see what they're asking in the next part. Part C says, use the empirical rule to determine the percentage of eruptions that last between 92 and 116 seconds. Hint, X bar sample mean is 104. Now, whenever they ask this kind of a question, it's always important to sort of catch your bearings. And what I mean by that is to figure out what do those numbers mean? What's 92 and what's 116? How many standard deviations away from the mean are those values? And so I'm not saying you have to, but typically what I would do is to draw a diagram, as you can see. Here's my diagram for this particular problem. So as you can see, I have the mean, which is 104 in the middle. And in part A, we estimated the standard deviation to be 6. And so if you go up 6 units from 104, that takes you to 110. And that would be mu plus sigma. And if you go up 12 units from 104, that takes you to 116. So mu plus 2 sigma. Similarly, if you go to the left, going down 6 units would take you from 104 to 98. That would be mu minus sigma. And going from 104 down to 92, that's a distance of 12 units, and that would be mu minus 2 sigma. So it's clear that what they're asking us here when they say 92 and 116, what they're really asking is how much of the distribution is within 2 standard deviations of the mean. And if you recall what the empirical rule says, the empirical rule says if you go out plus or minus 2 standard deviations in a bell-shaped distribution, you're going to capture approximately 95% of the data. And so that's the answer they're looking for to part C. It's approximately 95%. So as you can read, we expect 95% of the eruption lengths to fall between those two values, 92 to 116. And as you can see in the next part, they're going to ask us to verify that that's the case. So the question continues here with part D, and it says, determine the actual percentage of eruptions that last between 92 and 116 seconds inclusive. Now remember, inclusive means we would include the endpoints of that interval. All right. And you could count this directly. You can go back to the data set and count it directly, but it's probably easier to count it indirectly. There's less counting, in other words. So let's take a look at the data set once again. If you look carefully at the data set, you can see that there is a total of 44 observations. And that is going to be helpful because obviously if you're going to calculate a percent, you need to know what the denominator is going to be. And so we will be using 44. But instead of doing this the hard way, let's let the calculator help us, and we'll do this the easy way. So take a look at your calculator. I have the data set entered into list 1, and it's entered in the way that I took it from the table, and that's not how I want it. I want it to be sorted. It's going to make it much easier that way. So let's do that. I'll go back to the stat menu, and I'm going to sort it ascending. It doesn't matter whether it's ascending or descending, but whatever. Anyway, it's going to be list 1. And so let's go back and take a look at it. And so if you recall, we're looking for values that are below 92 or above 116. And so I can see right here that I have 90 and 90, 2 values right there. And so there are 2 values below 92, and then on the other side, you can see that there's a single value above 116. And so remember, we're including the endpoints. They said between 92 and 116 inclusive. So those values would be in. And that means we only need to worry about those 3 values that are not. And so we can calculate the percentage associated with those 3 values, or if you want to do it directly, since 44 minus 3 is 41, then that would suggest that there are 41 values that are included in between 92 and 116 inclusive. So let me quit this, and 41 divided by 44, that would be about 93%. So fairly close to 95, not exactly on the money, but fairly close. And so I think we can write that down. So what's the actual percentage between 92 and 116 inclusive? Well, as we saw, it would be 0.9318 as a proportion. And of course, if we change that to a percentage, we would multiply by 100. So I'd say, well, it's around 93%. Let's see what the next part of the question is asking. Part E is asking, use the empirical rule to determine the percentage of eruptions that last less than 98 seconds. So again, let's figure out, what is 98 seconds? What does that correspond to? Now previously I had drawn a diagram, and I don't really see any reason to draw it again. So here's the diagram from part C once again, and you can see that 98 corresponds to 1 standard deviation down from the mean. And again, the question was asking, well, what percentage are less than 98? So in other words, below 1 standard deviation, how much is there? Let's take a look at the empirical rule again. So we know that half the data values are below the mean and half the data values are above the mean. And however you arrive at this, you might notice that between the mean and 1 standard deviation, there's 68%. But if you go just on one side of the mean, half of 68 would be 34%. And so if you take 50 minus 34%, that would be 16%. And so that would be the amount that would be below 1 standard deviation. In other words, below 98. And so in this case, I really don't think there's any work to show per se. You can simply say that there's, no more than 16%, something like that. Let's put that down. And so you can see my response, and as I said, it's about 16% that we would expect to be below. Final question, part F says, determine the actual percentage of eruptions that last less than 98 seconds. So we're going to do that kind of like we did part D. We'll go back to the calculator and we'll see what's below 98. You want to go back to the data set. And it looks like I have 1, 2, 3, 4, 5. Count them, 5 values that are below 98. And so we can convert that to a percentage. And it's a little bit further off than the last one, but again, you have to remember that the empirical rule is an estimation. It's a rule of thumb, right? We're not saying that it's going to be exact every single time, and especially our data set here wasn't exactly bell-shaped. It was approximately bell-shaped. And so we want to jot this down, and as a percent, we would say, well, it's around 11%. As you can see. So the proportion would be 0.1136, and if we convert it to a percentage by multiplying by 100, we're saying it's about 11%. Hope that's been helpful. If you have any questions about this, feel free to drop me a line. Otherwise, feel free to go on to the next video.